Nice work if you can get it. Then moved to Los Alamos, where he's been ever since, first as a postdoc, working on what was called the Cygnus Array back then. And he was one of the founders of the Milagro experiment, became the spokesperson for Milagro, and then started the experiment that he's going to be talking to you about today, the HAWC experiment. In between, he managed to find time to collaborate with us on high-res at Dugway Proving Grounds. He's been a group leader at Los Alamos and is currently the Deputy Associate Director for Experimental Physical Science, I guess, and also the Director of the Los Alamos Neutron Science Facility. Not quite sure. Lance, right. He's also an APS fellow, so please welcome Gus Sinnis.
Thank you, Per. Yeah, and thanks for inviting me here. It's been a long time since I've been down here to the University of Utah, but I've always liked coming down here. So today I'm going to talk to you about some astronomy that we do out at 1 trillion volts, as the title says, with the detector that you see in front of you is called HAWC, for High Altitude Water Cherenkov Telescope Observatory. It's in Mexico, not too far from the city of Puebla, and that's a dormant volcano, not an extinct volcano, in the background called Pico de Orizaba. So I want to give people kind of an orientation on what the trillion volt astronomy is. And so this is the electromagnetic spectrum, right? So we have, we're starting here in radio waves. You have microwaves where you have the 3-degree background. You have infrared and optical where you see galaxies, right? And as you move up into the X-ray, MEV, GeV, and then finally you get out into the TeV. And the kind of objects that you see in there, it's not thermal, right? When you look out at the sky at night, if you just walk out at night and you look at the stars, what you're seeing is basically thermal radiation, right? Just things that have been heated up, gotten hot. When you're looking out at MEV, GeV, and TeV, there's nothing that just gets that hot and radiates in thermal. What you're looking at is particles that have been accelerated. So somehow, so like things are accelerated at Fermilab or at CERN, you're accelerating particles to very high energies, to TeV, similar to the LHC. And the objects that you typically see are compact objects, so neutron stars, black holes that are accreting objects. We actually haven't seen any gamma ray bursts yet in TeV, but you see those in the GeV range and the MEV range, and something called active galaxies, which are powered by gravitational inflow of material, so they can be black holes of 10 to the 6 to 10 to the 10 solar masses, accreting material on them. And then typically they'll have jets, highly relativistic jets coming out from them where the particles are accelerated up to TeV and beyond in energies. So today I'm really not going to talk about the extragalactic piece of things. I'll talk about that more tomorrow. I'm going to concentrate on things that we've seen within the galaxy with HAWC. So why do we do this kind of physics? Right? So there's really 3 main reasons. One, kind of the primary reason, is to understand how does the cosmos accelerate particles to these kind of energies. Right? It's not easy for us to do it here on Earth in very well-controlled environments. How do you do it out in the universe? Right? How does that get done? And then part of that is explaining the origin of the cosmic rays that we see. Right? We're constantly bombarded by high-energy particles here. How did those particles get accelerated? Where did they come from? You can also do some understanding of the extragalactic piece. You might be able to find the origin of ultra-high-energy cosmic rays. And then you just want to understand these astrophysical processes. Right? When you have this supermassive black hole, you've got a lot of material flowing in. How does this jet form? Right? That's not really a very well understood process. And then once that jet forms, how does it accelerate those particles? So you can do a lot of physics aside from just that astrophysics, right? So there's something known as the extragalactic background light. So if you look at, everyone knows about the cosmic microwave background, right? That's the kind of the echo of the Big Bang. What people don't know about is there's also light at shorter wavelengths, right? Higher energies. That comes from this mostly infrared light and starlight, and so a lot of it started in the very early universe, when galaxies formed, you emitted light, and then that light got absorbed by dust, re-radiated in the infrared. So if you can measure that light, you can say something about star formation in the early universe and galaxy formation in the early universe. So that's another thing that you can do with this kind of astronomy. And then you can also do some beyond the standard model physics. So I'll talk a little bit about this kind of at the end, as kind of the punchline. The searching for evidence of dark matter, right? So the universe is made up 75% of dark energy, 23% or 22% of dark matter, and a few percent of the stuff that we're familiar with. And so one of the big questions is, what is this dark matter? And so there are ways of looking for it using TeV astronomy. If you see flares from active galaxies, you can use those flares to try to measure the intergalactic magnetic fields. So this is a topic it's very hard to measure these fields. This is in between, in the big voids in the universe, what is the magnetic field in those voids? Okay, and how did they get there, right? How did these magnetic fields form? And the thinking is that they maybe formed in the very early universe, right near around the Big Bang, if there was a phase transition, and then they got amplified through dynamo processes during the universe. And so this tells you something about, if you can do this measurement, something about the primordial magnetic fields. And then you can look for violations of Lorentz invariant. So you have these objects that are very distant, right, 10 billion light years away. And you have light that comes that's in the optical wavelength, and you have gamma rays that can come in the GeV, 100 GeV energy range. And you can measure their arrival time and say, does it take longer for these different energy photons to get to us? Right? I mean, if everything is Lorentz invariant, then it shouldn't depend on the photon energy, how fast they travel and how long they get here. But you can basically look across the universe and time the travel of light to within a second or better. Right? So you can get very strict limits on Lorentz invariance.
So the universe has a dielectric constant of 1.
Maybe.
Exactly everywhere.
Maybe. Okay, so I mean, so that's an open question, because in quantum gravity theories, there's actually there are quantum gravitational theories where, in fact, that's not true. There is an index of refraction to the vacuum, and so that's the kind of thing that you're looking for.
But I would think there's an index of refraction anyway, because there's hydrogen anywhere, and if it travels 10 billion light years, there's so much hydrogen that this 10 to the minus something dielectric.
That actually is smaller effect than what we're looking for here. Yeah.
Okay.
So what kind of telescopes are there? So when you're up in space, there's instruments that can directly measure the photons coming in. And so Fermi is an example of that, and that's what's pictured here. So they measure gamma rays coming in. They have some material to convert those gamma rays into electrons, and then they can follow the electrons. The nice thing about being out in space is that you can surround your instrument with scintillator, and then if a charged particle comes in, you can veto on it. Okay, the charged particles in the cosmic rays outnumber the photons by 1,000 to 1 or more, and so you need to be able to reject those cosmic rays. So these are very small. So Fermi is about a square meter, because you just can't put a lot of mass up in space very easily. But they're essentially background free, and they do have a large aperture. They look at a big fraction of the sky, and they can operate continuously. But because they're small, they have a limited energy range. As I'll show you later, the energy spectrum of the sources of these kind of very high energy gamma rays falls off very steeply. So if you're up at a TeV, you're looking for, particles per football field per minute kind of rates, and so you can't see them in detectors this small. On the ground, there's two basic types of instrument used. There's something called the Atmospheric Cherenkov Telescopes. And so I'll show you some images later about how air showers form. But when a high energy particle comes into the atmosphere, it creates what's known as an extensive air shower, where you can get thousands or millions, or if you're dealing with energies that Pierre and his colleagues deal with, even billions of particles. And those charged particles in the atmosphere generate Cherenkov light in the atmosphere, because they're going faster than the speed of light in air. And these instruments pick up that and focus that Cherenkov light. So they're typically big optical dishes focusing onto very fast photomultiplier tube cameras. Okay, and they're looking for blips in the night sky background that last for a few nanoseconds, a few billionths of a second. So these are pointed instruments. They have very good background rejection, as I'll show you, but they have a small aperture because they're pointed, and they can only operate on moonless nights. So they have a relatively low duty factor. So the other type of instrument is what I'll be spending most of the talk talking about, and that is particle detection arrays, or extensive air shower arrays. So here you're measuring the particles that make it to the ground from this air shower. So you can operate around the clock and year-round, so basically 24/7, 365 days a year. You basically have the whole sky as your aperture, and I'll show you how we do that in some later slides. And so you have a large area, a large aperture, and a large duty cycle. So it's good for surveying the sky and monitoring sources. So if you don't know where a source is, you don't know where to point, right? It's hard to use this kind of an instrument to discover new sources unless you get some other clues. In here you can just do a survey of the whole sky as the Earth spins around, or the swath that you can see from your latitude. Okay, so extensive air showers. So Pierre Auger was the person that first discovered extensive air showers. And this was a paper published in 1939 where he first discussed that. So this is actually Pierre Auger over there peeking out from here, and this is Paul Ehrenfest. So they're in the, I think they're in the Jungfrau here doing their experiment. So it doesn't look like a very great place to work, but that's how things work.
Views are probably pretty good.
Huh?
The scenery might
The
be.
scenery, yeah, the scenery is very good. So what they measured here is this is the distance in meters on a logarithmic scale. So here is, 0.1 meters, 1 meter, 100 meters, 300 meters, and this is the particle density they measured. And so they saw that these showers were huge, right? It is much bigger than they were thinking about it, so out beyond 100 meters. And so then you can make some rough estimates of what kind of energy must be when you sum up all the energy of those particles, and it's covering that big an area on the ground, what kind of energy you're dealing with. And so they realized that they were looking at cosmic rays with energies of at least 10 to the 15 electron volts, right? And as I say here, it seems that they didn't really understand how can you possibly have a single acceleration site that can accelerate a particle to those energies. And so they didn't understand that, and they said it's much more likely that they acquire their energy along these very long electric field lines, okay, which is in fact not correct. But that was their original thinking. So what is an extensive air shower? So say a proton comes in, has an interaction with an air nucleus, breaks up the air nucleus and creates pions, right? Pi zeros, pi plus, pi minus. The pi zeros decay into 2 photons very fast. The pi pluses and pi minuses decay into muons, mu plus and mu minuses. And then they propagate down. And then those gamma rays, they have further interactions, and so you just develop a shower, right? So every radiation length, you can double the number of particles. You get to a point, and that's what this curve is. It's the number of particles is on the x-axis, and then this is the depth through the atmosphere. And the number of particles builds up and builds up. But once, because the main energy loss mechanism is to create more particles, but once the average energy per particle is about 80 MeV, then the energy loss mechanism becomes ionization and things like that. So then the particles start to get absorbed by the atmosphere and die off. And this point of shower maximum depends on the energy of the particle and the type of particle, whether it was a gamma ray, a proton, an iron nucleus, or something like that. So this is a Corsica image of the development of an extensive air shower. So on the left is 100 TeV photon, on the right is 100 TeV proton, and you can see here that the electrons, which counts gamma rays as well, is in red. So that's mostly what the air shower is. It's actually mostly photons, mostly gamma rays, and the muons are in gray. And so if you look over here, you don't see very many muons in the gamma ray shower, but you do see muons and neutrons in the proton shower. Okay. And you can see that it's very thin, this particle front. So when you get down to the ground, you basically have a pancake that's 100 or so meters across, but it's only about 1 meter thick. Okay, and so it takes a few nanoseconds to pass by your detector. And that's how you can pick it up from the random starlight and such if you're in imaging air Cherenkov telescope, or just from your single trace if you're in an air shower array. So the gamma ray showers are almost purely electromagnetic and they're relatively compact. This is what it looks like if you just integrate it over all that time. You can see the number of particles is building up and then dying down, and this is the gamma ray shower. And then here's the proton shower. You get a lot more, you get a lot of these sub-showers coming out from pions that go out. They both have a core of energetic particles, but if you're in a ground-based detector, you need some way of distinguishing between these two. Okay, and this is spread out very far, so I'll talk more about how we do that. In some sense, it's kind of like doing astronomy during the day.
Are these pictures supported by actual experiments, laboratory or on-Earth experiments?
So what we do is, so certainly the development of them is supported by the imaging atmospheric Cherenkov telescopes. They actually have cameras that can watch this longitudinal development of the shower at very high energies. Things like high-res and TA with the air fluorescence detectors can watch this longitudinal development of the shower. What we can look at on the ground when we have a surface array like HAWC, we can look at what is the particle distribution, the longitudinal distribution on the ground, and that, or lateral distribution on the ground, and that matches with these simulations as well. So the electromagnetic simulations are pretty straightforward, right? It depends on what the atmospheric density profile is, but aside from that, the physics is well understood. The hadronic interactions, especially as you go to very high energies, the energies that Pierre and Gordon's group are dealing with, are not as well understood. Okay, so you see some anomalies in those very high energy showers. So this is what an atmospheric Cherenkov telescope looks like. So you have this gamma ray coming in, and it makes this shower of particles, and those shower particles generate this Cherenkov cone. It's very forward beam. The opening angle of the Cherenkov cone is about 1 degree. And then this is and it illuminates about 100,000 square meters on the ground. So one telescope can see things very far away and have a very large effective area, we call that. And that Cherenkov flash, as I said, lasts for a few nanoseconds. This is images from the MAGIC telescope of different events that come in. Okay, so the position on here has to do with angle, and so that's how you get the longitudinal development of the air shower, because different angles now will come in at correspond to different altitudes. And so these rings are due to muons. And so when you see a ring, you know there was a muon in the shower, and therefore it was not an electromagnetic shower. So you can reject those events. They also are looking for events that point towards the center of the camera, because that's where their source is. And so any of the events that didn't point towards the center of the camera, they can also reject. So they can reject over 99% of their background and do a very nice job in detecting these high energy sources. And so this is an example, 2 examples of modern arrays. The Veritas array, which I know some people here in Utah are working on, has 4 telescopes. It's over in Arizona. And then the HES detector, which is in Namibia, had 4 telescopes, and they added this giant telescope that's over 20 meters in diameter. So a very impressive piece of equipment. Just absolutely, this is actually a picture. Right? So it just dwarfs the other telescopes. These telescopes are about the same size as the Veritas telescopes to set the scale. So for an extensive air shower array, this is a picture of an array that's up in Tibet, in well, what some people would call China. I don't want to get involved in that. So it measures about 200 meters by 200 meters, and these counters are scintillators, right? So they're about a square meter of scintillator, but the thing to notice is that most of the area enclosed, there's nothing, right? There's nothing instrumenting it. And this is now a Corsica simulation, again, 200 meters by 200 meters overlaid, and this is a particle distribution from an air shower. Right? And so you can see that it's actually pretty spread out, and most of these particles wouldn't get detected. In essence, the array is covering about 1% of the area, so you'd only detect 1% of these particles, which means that your energy threshold is maybe a factor of 100 higher than it needs to be. Okay, so the big advance that we made back in the early 90s was to realize that if you use water as a detection medium, that you can actually get almost 100% coverage of the area. And the reason for that is that the Cherenkov angle in water is about 41 degrees. And so if the depth of your photomultiplier tubes is comparable, or half of the spacing between them, then you're sensitive to particles that come anywhere into your detector. Okay, so you can automatically lower the energy threshold significantly by using water as the detection medium, and that's what we did here. And this second layer is to pick up the penetrating component, the muons that come in the shower, and distinguish between the hadronic showers, the proton-initiated showers, and the gamma-ray showers. Okay, so, and the other thing that's nice about water, as I said previously, that the showers are actually mostly gamma rays, about 6 to 1. And so water will convert the gamma rays in the first foot or so, and then the electrons that they're converted into will generate Cherenkov light that you can pick up. Okay, so background rejection. These are images of particle showers of different energies. The top are gamma ray showers, and the bottom are proton showers. And the big difference, the red dot is where the core, which is where the primary particle, the primary cosmic ray, would have hit the Earth if the atmosphere wasn't there. That's what's known as the core of the air shower. And that's where the most energetic particles tend to be. But you can see the gamma ray showers, as we showed before, are nice and compact, whereas the proton showers have a lot of these sub-features. And so you can use this, and a lot of these are due to muons. Okay, and so this is how we do the rejection in an extensive air shower array. So how do we do the angular reconstruction, right? So we're looking at the whole sky. This pancake is coming down, and so if you measure the arrival time of the pancake as a function of position on the ground, and this is data taken with the Argo detector, which was one of the detectors that's up in Tibet, you can see that it forms this very nice plane. And then the perpendicular to that plane points you back to the direction where it came from, right? So the charged cosmic rays all get randomized, and the gamma rays are coming straight from their source, undeflected, and so you look for excesses in certain regions over this kind of smooth background that you get. Then to measure the energy of the air shower, now we're measuring the tail end, right? We're down here on the ground. If you remember that picture from the Corsica picture, a lot of the particles didn't make it, right? So we're kind of getting what would normally come out of the back end of a calorimeter if you're running a high-energy physics experiment. Okay, so we don't do that great. We can measure the energy on the ground very well, but interpolating back to what the actual primary energy is not as easy, and our energy resolution is something like 40%, mostly dominated by fluctuations in the development of the air shower. So the instruments that exist, so Milagro was the first water detector. This is really the first extensive air shower array to see an astrophysical source of gamma rays. And now that's no longer operating, and we're operating HAWC. And then there's Veritas and HESS that I talked about, and MAGIC is over on La Palma. And then the Tibet Air Shower Array and Argo. And Argo is no longer operating, but the Tibet Air Shower Array is. So there's not a lot of these experiments around the world. It's just a few of them. Okay, so cosmic ray origins, as I said, is one of the reasons that we want to study this kind of physics. So this is a picture of Victor Hess going up in a balloon. So when radioactivity was first discovered, the question was, where is it coming from, right? I mean, people they discovered it because they put a photographic plate in their drawer, and then they took it out later and they saw that it was exposed, and they had to get it exposed. And so people built these instruments called electroscopes, where you took two gold leaves, you would deposit a charge on them, they'd separate because they had the same charge on them, and they noticed that over time, the gold leaves would come together. And how was that happening, right? And so they did all kinds of investigation, measure the resistivity and the silk thread that they used to hang the gold leaves, and they determined that can't be the cause of it. And so the idea was, okay, there's some residual atmosphere inside of this thing. Particles are coming through and ionizing that atmosphere, and that's providing a current path to discharge the leaves. And so then the big question is that radioactivity coming from the ground, or is it coming from space? Right? And it took a long time. People would go up on mountains, but of course you're still near the ground when you go up in a mountain, so that didn't really help a lot. But then when Victor Hess went up in a balloon, he noticed that, so when he went up to 5 kilometers, no supplied oxygen. And this is the curve he measured of the ionization using one of these electroscopes. Okay, so in fact, which made it also harder, it dropped off in the first kilometer, right? So people would be misled if they, I know people went up the Eiffel Tower as well to make these measurements, and then finally proved that in fact these particles were coming from outer space. And this quote is taken from his Nobel lecture. No one has yet been able to provide any detailed explanation about how these rays get generated. 1,000 times more powerful than the strongest radioactivity. So how are these particles accelerated? So this is a paper 1949 published by Enrico Fermi, and this was his idea, was that what's happening is that particles are being reflected by magnetic clouds that are in the galaxy. And if you've ever been in a rainstorm, you notice that more rain falls on your front windshield than on your back windshield, right? And it's a very similar thing here, that just the probability, because when you're going in a certain direction, if things are falling straight down, more things are hitting you in the direction that you're going. And so the idea is that there's more forward-going collisions than backward-going collisions. So if you have a tennis ball hitting a wall, and that wall is moving towards you, the tennis ball comes off of the wall with more energy than it went in. If the wall was moving away, it would come back with less energy, right? And there's more of those forward collisions, so eventually the particles can get up to very high energies. So that's known as second-order Fermi acceleration. Okay? It's a very inefficient process, and that's probably not how that, well, we're pretty sure that's not how things get accelerated now. So what do we know? So this is the cosmic ray spectrum, starting at a GeV and going up to over 10 to the 20 electron volts. And to first order, it's falling very, very steeply, right? The spectrum is something like e to the minus 2.7 in this region, and steepening to e to the minus 3 or so in this region. Okay, so that's been very well measured. We also know that the galactic energy loss, so we can measure the lifetime of the lower energy cosmic rays because there's radioactive material in cosmic rays, and so we can measure how long they've been trapped in the galaxy. And when you do that, you can say that the energy loss is 10 to the 41 ergs per second. So you need to have an energy source that puts things into equilibrium, so you need an energy source that corresponds to around 10 to the 41 ergs per second. So the first thing people thought of, in fact, was supernova, right? So if you look at the energy budget of a supernova, it's 10 to the 51 ergs. If there's one every 30 years, that corresponds to 10 to the 42 ergs per second. So if you have 10% efficiency in converting the kinetic energy of the supernova into cosmic rays, then you found the source of cosmic rays. Okay, so this nice numerical matchup had people suspecting for a long time that it was supernova that were accelerating the cosmic rays in the galaxy. The other thing that supernovae do is generate strong shocks. And so the thinking now is that the way you accelerate the particles is by what's called first-order Fermi acceleration. So when you have a shock and it's moving out, the particle, every time it crosses that shock, picks up energy. And that's why it's called first order. It's not depending on a probabilistic thing. Right? You have diffusion of the particle and it gets trapped by the magnetic field, and so it comes around and crosses a shock many, many times. Eventually it gets to a high enough energy that the Larmor radius of the particle is greater than the radius of the shock, and it can escape, and then it becomes a cosmic ray. So everything kind of hung together, and you do the calculations, the maximum energy you can get out of such a system when it starts to leave is about 10 to the 16 electron volts, which wasn't too far from this knee region. But it's been very hard to find direct proof. Okay, so backing up a bit, now we have these high energy particles, how do we get photons out? Right? So we want to be able to get photons out. So there's a couple of ways to get photons. So if we're accelerating protons, it's pion production, right? Proton-proton collision generates pions, the pi zeros give you the gamma rays. Okay, in the rest frame of the pion, the pi zero, the gamma rays have about 70 MeV of energy. If you have electrons, there's three main mechanisms. There's synchrotron radiation that I think everyone's familiar with. An electron goes around a magnetic field, it emits synchrotron radiation. Right? So if a strong magnetic field and a high energy electron, you can actually get fairly energetic synchrotron. You can get synchrotron X-rays. Inverse Compton scattering, you have a high energy electron hitting a low energy photon, and the electron transfers most of its energy to the photon, and you can boost that photon to TeV or more energies. And then you also have electron bremsstrahlung, right? When the electron is accelerated in the field of a nucleus, it'll generate a gamma ray. Okay, so what are the galactic gamma ray sources that we know of? There's quite a few. 35 pulsar wind nebula. The most are unidentified. Okay, so they've been seen by TeV instruments, and it's hard to say this is this specific source because there are so many X-ray sources in the sky that within the point spread resolution of one of these instruments, you'll find many X-ray sources. So it's hard to pin down which one it is, and so that's why most of the sources are actually unidentified. So this is an example of a pulsar wind nebula, and I'll talk a lot more about those later. You have X-ray binaries, you have supernova remnants, you have supernova remnants hitting molecular clouds. So almost everything that we know of. There's a lot of things now, even the cataclysmic variables, and we've even detected TeV gamma rays from a globular cluster. So there's a lot more sources than we thought would be when this first started. The first source was actually discovered in 1990, and that was the Crab Nebula. And since then, things have progressed relatively quickly. So, cosmic ray origin. So, this is a supernova remnant, RxJ 1713. And it's an image from the HAWC telescope. So, this is a TeV image of that remnant. So, this is where most of the TeV gamma rays are coming from. And what I'm going to show you next is an overlay of an X-ray image. Okay? Hopefully. That didn't work. Okay, so if it did work, what you would see was that the X-ray image almost exactly sits on top of the TeV image. Okay, there's a beautiful correlation between the two, which is telling you that the source of the X-rays is the same as the source of the TeV gamma rays, which is telling you that it's probably inverse Compton scattering, right? That the X-rays are being formed you're coming from synchrotron radiation of the electrons, and then the TeV gamma rays are coming from inverse Compton scattering of those electrons and the synchrotron X-rays. Okay, so we call that synchrotron self-Compton. Okay, and so that's saying, okay, this is not a source, this is not protons doing this. Or it may be, but there's a lot of gamma rays created by these electrons, so we can't prove that it's protons doing this. Okay, here we go. This is the X-ray image. So, okay, so now you can see, in fact, that this will morph into it. And you can see they're very, very similar.
What's the thing in the middle?
So, there's the source of, so it's probably not in the middle, right? This is a projection on the sky. So it's probably from the shell that's coming towards us. Okay. So, as I mentioned before, when you're producing pions, a pion's 140 MeV in mass, and so if you can see something that we call the pion break, where you can see photons coming out at 70 MeV, that's what you need to prove that there's protons there. And so what we're seeing that, this is from Fermi data on a supernova known as W44, relatively close by, within 3 kiloparsecs. It's only 10,000 years old. This is the spectrum that they measure, and there's this break down here at a few hundred MeV. So it's in the rest frame of the pion that they're 70 MeV, but the protons are high energy, right? And so things are boosted, and that's why this break is not at 70 MeV, but at a few hundred MeV. And so you have to fit simultaneously the proton spectrum with the gamma ray spectrum. And this is the spectrum you get when you do that. If you try to fit it with electron bremsstrahlung, you get something that doesn't fit the data. So there was this source, and there was one other source that you clearly can see this pion break. So we at least know that some supernova remnants are accelerating protons and producing the cosmic rays. So pulsar wind nebula. So what these are, this is a picture of the Crab Nebula. So the pulsar is in the center here. You can actually see some jet structure, and the pulsar is spinning around very rapidly, right? They can spin around up to, I think this one is at 30 hertz, 33 hertz, something like that is the Crab Nebula. And then they accelerate, and I'll talk more about that in some next slide. But it's the most common source of galactic TeV gamma rays, okay, as we saw, except for the unidentified. And a lot of the unidentified are probably pulsar wind nebula. And as I'll explain later, they can inject positrons into the interstellar medium, and this is important because this can be a background for dark matter searches, and I'll talk about that in this talk. Some surprises we've had, that we've detected pulsation from the Crab pulsar. So first we just saw the nebula, but Veritas has seen pulsations coming out over 100 GeV in energy, and Fermi has actually seen strong GeV flares. So people thought, if you look at the size of the nebula, and if you say the electrons are all out here giving you inverse Compton gamma rays, it's hard to see how you can get a flare in very short duration. So that was a big surprise. And people are still trying to figure out how that works. So this is kind of the basic structure of a pulsar here. So it's a rapidly spinning neutron star. At the surface of the star, the magnetic field is 10 to the 12 Gauss. Right? So when you spin a magnetic field of that strength that rapidly, you generate an electric field. You start pulling electrons and positrons out of the pulsar and even out of the vacuum. Okay, and those electrons then form a wind termination shock. Okay, and at that shock, just like in a supernova shock, you can accelerate these electrons and positrons to much higher energies. So inside here is where the pulsar wind nebula is, and this is the nebula, and then so this is kind of the supernova shell going out, and then this is the reverse shock that comes back in. And so at some point that reverse shock will then crush the pulsar and then crush the nebula around the pulsar. But the other thing happens is that these pulsars are actually born with a kick. Okay, so I'm not sure what the exact reason, I don't know if anyone knows the exact reason. I know Sterling Colgate at Los Alamos believed that it was neutrinos forming that, but it could be something more of a hydrodynamic instability, making things in the actual explosion not symmetric, right? And so, but they're born with velocities between 200 and 500 kilometers a second, right? So this is something 1.4 times the mass of the sun moving at 200 to 500 kilometers a second. That's pretty impressive, right? And in fact, I think the highest pulsar kick observed is about 1,100 kilometers per second. So these pulsars can actually leave the supernova remnant. Okay, and then you can regenerate the wind and the nebula around the pulsar. And the idea is that there's a magnetic field around that pulsar, and it's kind of keeping these electrons and positrons where they are. But over time, as the nebula expands, the magnetic field weakens, and it releases those positrons, electrons, and puts them into the interstellar space. Okay? So keep that in mind as we go through the talk. So now I'll digress and talk a little bit about what we've done with HAWC, and then I'll loop back to the pulsar story. So this is a picture of the detector. We have 300 water tanks. The tanks are 4.5 meters high by 7 meters across. They have 4 photomultiplier tubes in them. The whole area here is about 22,000 square meters. So we're up in Mexico, 19 degrees above the equator. The elevation is 4,100 meters, and as you saw before in that picture, it's important to be high up because you want to be close to the shower maximum as you can. And we have, this whole area is essentially a muon detector now. So 22,000 square meters of muon detection area, which is about 10 times what we had in Milagro. And so the whole instrument is about 10 to 15 times more sensitive than Milagro was. And this is the collaboration. This is a picture up in the Upper Peninsula of Michigan, the Agnostic University. Okay, so this is a picture of the tank with Brenda Dingus, a Los Alamos scientist. So we don't have any hardware trigger. We read in every single hit in all of those PMTs, all 1,200 PMTs, We have a data rate of about 500 megabytes a second, and we form the trigger in software, looking for many hits in a short period of time, in a few hundred nanoseconds. We keep all the data for 24 hours, and then we start, so if someone tells us, hey, we saw something from this part of the sky, we can take that and maybe apply a lower threshold than our trigger, normal trigger is. And then we keep all of the reconstructed data, which is about 600 terabytes a year. And this is what the inside of the tank looks like. So there's 3 photomultiplier tubes out here, and a bigger high quantum efficiency photomultiplier tube in the middle. This is what a typical event looks like, and the color scheme corresponds to the pulse height, how much charge was collected on the PMT. And so here you can see this is where the core of that air shower was, and then the charge dies off as you move away from that core. And this is a very non-typical event. So this is an event that came essentially from the direction of the Crab Nebula, very high energy, 60 TeV, and we classify this as a gamma ray event based on its topological structure. So we don't see any evidence of muons or subshowers out there. And so, but it's lit up essentially every detector in the array. And so this is the background rejection. So we're looking for, if you want to call it a proton, you're looking for large pulsites far away from the core of the shower. So this ring is 20 meters around the core of the shower, and you can see in the proton showers you see things out there, in the gamma ray showers you don't. And when we apply that, this is the rejection parameter that we use, where gamma rays are over here to the left, and so this blue curve is what we get when we look at a bin near the Crab, but not at the Crab Nebula position, and the dots are what we get when we look at the Crab, and so this is the signal that we see from the Crab Nebula in this data set. So we've done a good job here, a very high signal to noise, which before HAWC it was not done in extensive air shower arrays. So when we look at the whole sky, what do we see? This is what we see. So we have the galactic plane over here. We have the Crab Nebula over here. And Markarian 421 and Markarian 501 are 2 extragalactic objects. So these are 2 active galactic nuclei. And when we look only at events with energy above 50 TeV, we see a lot less, but we still see something, right? So there's still things that are active above 50 TeV, essentially all in the galactic plane. It's hard to see, but actually we do see the Crab Nebula above 50 TeV as well. But those extragalactic sources have completely disappeared. And this is what the Milky Way looks like if we just blow up around the Milky Way. So you see a lot of sources. We saw almost 40 sources, half of which hadn't been seen before. And so this is the catalog that we put together. 7 of them we identified as pulsar wind nebula, and the question is, are these now sources of the positron excess, which I'll talk a little bit about. And this is just a plot. The red ones are new discovered sources. The gray circles are sources that we knew about, and the circle says you how big those sources are, and this is their strength, and this is how quickly their energy, the flux is falling off with energy, what we call the energy spectrum. So pulsar wind nebula. So we observe pulsar wind nebula as extended objects. This is Gaminga. Gaminga was first discovered in gamma rays. In Italian it means not there, because no one had seen it before. And it was discovered as a pulsar in gamma rays, lower energy, MEV gamma rays. We see it, it's very extended. It's a few degrees across, right? It's 4 or 5 degrees across, kind of 2-degree half angle. Air Cherenkov telescopes have looked in this region and they don't see anything. And the reason for that is that they have a very small field of view. Their whole field of view is only 3 degrees or so. And so the way they do their background rejection is they look at the number of events as they move away from the source, but if the source is bigger than their field of view, then that's flat and they say we don't have anything. Okay, so they're essentially insensitive to sources like this. And then there's this little neighbor here known as monogem. Pulsar is B656 plus 14. Okay, so this is again another pulsar wind nebula, and there was a paper recently by Tim Linden and Dan Hooper that's out on the archive where they're saying that the sources that we discovered is really a new signature of pulsar wind nebula, this TeV halo that's surrounding the pulsar wind nebula, very large halos. And the halo is produced by inverse Compton scattering of these high energy electrons that are accelerated at the wind termination shock, interacting with the cosmic microwave background. Okay, so they're streaming away from the pulsar, interacting with the 3-degree background, boosting those 3-degree background photons up to TeV energies. And it then radiates into 4 pi. So most pulsars are discovered when you're looking right at the jet that comes off of them. That's the flashlight or the
Beacon.
the beacon, right, as it's going around. And so if you're not looking at them, most of them are probably undiscovered, right, because that beacon is fairly narrowly pointed. Okay, so the expectation is, in fact, that as we operate, we'll discover many more of these. And so they put this plot together that shows our sensitivity versus the sensitivity of an imaging atmospheric Cherenkov telescope. And so this is the distance, and this is the spin down energy. So the energy that's powering this thing is the braking force from the pulsar spinning down, right? And so what you see is when they're close by, they're big in the sky, right? Which means that the atmospheric Cherenkov telescopes don't have any sensitivity to them because they're bigger than their field of view, whereas we have very good sensitivity to them. So we're orders of magnitude, 5 orders of magnitude more sensitive when something is very close by. And as it gets more distant, we get less sensitive and they get more sensitive. So there's this kind of whole unexplored region now that we're sensitive to. And so that's why their expectation is that we'll discover many more of these pulsar nebulae. So backtracking a little bit and to tell the story, dark matter. Right? So as I said, right, most of the universe is actually something called dark energy, right, which we know because when we look out at very distant galaxies, the velocity with which they're moving away from us is getting faster and faster as you go more distant. Right? The universe is accelerating, and what's responsible for that is the dark energy. That's 73% of the energy density of the universe. What we see and what we normally deal with are atoms. That's about 4%. Right? And the rest is 23% is what we call cold dark matter. Okay, so it's non-baryonic and it's not luminous, right? And so the only way that we've observed it so far is through the gravitational interactions, looking at rotation curves of galaxies. And if there was no dark matter, you would expect the rotational velocity to fall off as you went away from the center of the galaxy. In fact, what you see is that it's pretty flat, which says that there's matter there that you're not seeing. So one of the leading candidates is something known as weakly interacting massive particle, and so this would be something predicted by supersymmetric theories to exist. And if you get this particle and its antiparticle annihilate with each other, they can produce gamma rays, they can produce electrons and positrons, and such, and so we can detect them in the cosmos by looking for these gamma rays or looking for positrons, antiprotons, things like this. And so this dark matter annihilation can produce these high energy positrons. So Pamela made the first really clear detection of this. This is the positron spectrum near Earth, right? Taken in the satellite. This is actually the AMS, which is on the space station. And the red dots are their data, and it's the positron flux times E cubed, which is why it's going up. It's really falling, right, but with energy, but we multiply it by E cubed, and you can see here 100 GeV, here's a TeV. You can see this positron flux quite high. What they'd expected to see was this green curve, and this is the number of positrons that you would see if the only production mechanism was secondary production of cosmic rays interacting with interstellar matter. And so the question is, where are these positrons coming from? So people got very excited. They said, it's dark matter annihilation. And then some other people came along and said, no, pulsars can be doing this, right, through the mechanism that I told you, that they trap these electrons and positrons for a while, and then they release them into the wild when the magnetic field gets weak enough. So what you want to look for are pulsars that are nearby and old. Okay, when the two I showed you are in fact perfect candidates for that. Geminga is 300,000 years old and is 250 parsecs away. Monogem is 100,000 years old and only 300 parsecs away. So if there was going to be pulsars that were supplying this positrons, these would be the places to look. So, are they supplying the positrons? So because we actually see the electrons, right, by looking at the inverse Compton photons, we're actually can measure the electron and positron distribution away from the pulsar, which says that we can measure the diffusion coefficient, how fast are these things diffusing away from the pulsar. And did they have enough time, given their diffusion coefficient, to reach Earth and be the source of the positron excess that we see. So this is, I'm not allowed to show the axis yet. But the paper was accepted by Science, and it should be published probably mid-November, it looks like, and then I'll be able to show you the axis. But this is the surface brightness that we then use to infer what the electron density is as a function of distance from the pulsar. Okay, and you can see it's fairly sharp. In fact, when we first saw this, a theorist at Los Alamos came up to me and said, the fact that you see it alone is enough to tell you that it can't be the source of positrons, right? Because if the positrons were here at Earth, the thing would be so big that we'd be in their cloud, we'd be in the inverse Compton cloud of the photons, and we wouldn't be able to see anything because now we'd have the same problem that the Cherenkov telescopes see, right? We're just completely surrounded by this. So we measure the diffusion coefficient, and then we run through our calculations. And so this is the AMSO2 measurement of the positrons, E cubed times their flux. And this is what we say our best guess is to what Gaminga's contribution can be to this positron flux. And monogem doesn't even show up here. Okay, so we can make a very clear statement that these two nearest and dearest pulsars are not the source of the positron excess.
This assumes that this positron production process is basically continuous. Like no episodic desert.
That's right. That's right. So there's no real reason to expect it to be episodic. So when we look at the Crab Nebula, it's in our energy range. It's very steady. Things are happening on very big distance scales here. The caveat, the trickier thing is, like I said before, we're looking at a two-dimensional projection. So we're really measuring the diffusion that's transverse to us. It's possible that the diffusion coefficient coming at us is different. It would be weird, but it's possible, right? So you can imagine maybe there's some very well-structured magnetic field that's connecting us to that pulsar wind nebula. Then you could say, okay, then the positrons can't get to us. But that's kind of a contrived model.
Are Gaminga and monogem in our galactic arm?
Yeah, so they're only 250 and 300 parsecs away, so they're pretty close, right? The galactic center is 10 kiloparsecs. So
No, but they're galactic arms.
Yeah, but I think that distance it has to be in our arm.
Can you remind me what's diffusing?
The electrons and positrons are diffusing, right? They're not just streaming out.
Real honest God diffusion, like
Yeah.
air molecules.
That's right, but they're diffusing through a magnetic field, right? Is typically what causes them to, because it's hard to cross a magnetic field line when you're a high energy particle, right? You want to get trapped by that field line and spiral around it, and so they just
Down the diffusion.
yeah.
So how complete do we have for this pulsar with nebula in the vicinity? How complete is the catalog for these kind of resources?
So my feeling is it's not very complete, right? Because we see more of them. I think a lot more than 7 of the things on our list are pulsar wind nebula. So actually in that paper by Hooper and Linden, they do a statistical analysis, and I think their conclusion is that we might be seeing more like 15 or 16 pulsar wind nebula. But these are the closest ones that we know of and the oldest ones. So it is always possible that when you sum up all of those pulsars around the galaxy, and when you find them all, maybe they are actually the source, right? So we can't say that pulsars are not the source of the positrons. What we can say is that it's very unlikely that these two are, and right now these are the two best candidates. But it may be that there are other ones that we haven't detected and other people haven't detected. Okay, so to summarize, I think the experimental techniques in my career, I've been at the laboratory for 27 years. What the first experiment that Pierre said I went to work on was the Cygnus experiment. We spent a lot of time seeing nothing. And then we developed the water Cherenkov technique, and we ran Milagro, and we saw a handful of sources. And now we've at the stage where we're seeing 40 things, and my guess is, we'll soon see many more things as well. So I think the techniques have really developed over the last few decades. We've learned a lot, but we know the origin of some of the cosmic rays, the lower energy cosmic rays, but we haven't found what they call the galactic pevitrons, right? So we can't explain the galactic cosmic rays up to the knee, because all of the gamma rays that we see, 50 TeV, that you saw that the sky wasn't very bright, weren't many things there. By the time you get up to 100 TeV, a PeV, then you don't see anything up there. And so the question is, where are these cosmic rays of those energies coming from? That's still unknown. So with the survey we've done, we found a lot of sources. We just found these halos around pulsars, and I think we've proven that these closest and oldest pulsar wind nebula cannot be the source of the positrons that AMS and Pamela have seen. So I think that kind of deepens the mystery of where these positrons are coming from. Thank you.